Mr. Upra. I would like to teach the concepts of statistical modeling today. We need to understand the type of data first before we can actually do a statistical modeling. We can broadly classify the data into 5 categories. Number 1, dichotomous data. Number 2, continuous data. Number 3, ordinal data. Number 4, counts and rates. Number 5, time to event type of data. Matthew, can you tell me what is meant by dichotomous data?
I'm not really sure of the meaning. Could you explain that to us?
Dichotomous data is nothing but there will be 2 outcomes, like for example, gender, male and female, mortality, dead or alive. So when you have 2 outcomes only, either male or female or dead or alive, can be coded into binary data and you can perform logistic regression. Similarly, a continuous data is a different type of data. So where it can range from 0 to infinity with the decimals. So a continuous data, you can do a linear regression if there's a normal distribution. The other type of data you encounter is ordinal data, where there is a hierarchy. There are ranks. Go to supermarket, you open the chili packet, mild hot, moderate hot, and severe hot. There is a labeling on it. So there is a ranks hierarchy that you can have scores like, for example, pain scores, mild pain, moderate pain, severe pain. There is a hierarchy and the rank is increasing as you go higher and higher. So with this type of data, you can actually do a ordinal regression. One more thing is the counts and rates. Counts and rates are nothing but discrete numerical data. Like for example, in day-to-day life, if you go to hospital, you get blood test done. So you get white cell count. It can range from 1 to several thousands. So those are examples of counts and rates.
So how does this actually differ between continuous data and this counts and rates?
That's a very good question, Matthew. So the difference between continuous data and counts and rates data is that in continuous data, you got decimal points. Like for example, heights can have 154.5 centimeter. But in the counts and rates, you can't have decimal points. You can't have 1 death, 1.5 death, 2.5 death. You can't have 0.5 death in any of the counts and rates. The other type of data we encounter, which is a special data, is time to event data. You got a starting period of time. For example, when a patient undergoes cancer resection, patient will be is under intense surveillance 6 months, 1 year, 2 year, 3 year, 4 year, and 5 year surveillance. If any event happen while he's under surveillance, such as recurrence or mortality, then that is classified as an event, time to event. This can be applied even for the benign conditions. If a patient comes to A&E with angina, and if you started an aspirin or clopidogrel for rest of life, if you wanted to see if he gets another attack of angina or myocardial infarction, so if you can do a surveillance 6 months, 1 year, 2 year, 3 year, 4 year, and 5 year, and see if there is an event like an angina or an MI happened. If an event happens, that means it's a failure. More number of failures, the more events are. So that is how the graph represents in a time to event data. Time to event type of data, we do Kaplan-Meier survival analysis. So depending on the type of data, we can do different types of equations. So now I'm going to go a bit more depth into dichotomous data. Statistical modeling for dichotomous outcomes. What are the statistical tests you can perform? For example, risk ratio or relative risk is nothing but risk of event happening in an experimental group with that of risk of event happening in a control group. And the other concept is odds ratio. Odds ratio is nothing but odds of event happening in experimental group with that of odds of event happening in that control group.
So, could you give us an example of odds ratio data set so we can better understand?
So the best example I can give is smokers and lung cancer. So the odds of getting lung cancer in a smoker is 30:1 if you compare with that of non-smokers. So then comes the concept of risk difference or absolute risk reduction. Is nothing but risk of event in experimental group. If you subtract risk of event in control group from risk of event happening in experimental group, you get risk reduction or absolute risk reduction or risk difference. Why is it so important, risk difference? Because it helps us to calculate number needed to treat. So what is this number needed to treat? This is the minimum number of patients required to see a single effect of the treatment. That is what is number needed to treat. To do statistical modeling for dichotomous outcome, as we know, we can only divide whether an event happened or not. So if an event happens, that is counted as a success. If the event hasn't happened, then that is counted as a failure. So what you need to do is you need to draw a 2 by 2 table. Experimental, control, and any other comparative intervention you want to do. So divide them into event and no event. And then do logistic regression to see if there's any difference between an experimental group, a control group, or any other interventional group.
So, sir, why do we use logistic regression for dichotomous data?
Dichotomous data by itself is not a normal distribution. What log function does is it deflates the values. If there are any peaks in the data, ups and downs, it actually reduces or deflates. For example, log of 100 is 2, log of 1000 is 3, log of 10 is 1. If you really wanted to see the difference between experiment and a control, unless there is a big jump from 10 to 1000, you can't see a significant difference because log 10 is 1, log 100 is 2. So there is no much difference between 2 and 1 when you log transform the values. But if there's a significant difference, for example, if there's a values in the experimental group have jumped from 10 to 1000, so there is a difference of 2, then it becomes statistically significant. That's why log transformation helps us to understand the differences in the outcomes. If you go and fly in Dubai, from a bird's eye view, if you look at Dubai, the only tallest building that you can see is Burj Khalifa. All other buildings, although there is a discrepancies, they all appear like a flat buildings. That means that you can make it out that only the Burj Khalifa is tallest. That is what the log transformation is like. It's a bird's eye view looking at your data to see if there's any difference between experimental and control. Statistical modeling for continuous data. We use linear regression function for statistical modeling of continuous data. Continuous data can range from 0 to infinity with decimal points. So if you look at the graph here, we can plot all the independent variables on the x-axis and all the dependent variables on y-axis, and to see if there is any relationship between x and y, and create a straight line if there is a relationship. That is what is a linear regression is. The concept of linear regression is applied for normal distribution.
So, sir, in what other situations can we use linear regression?
In a t-distribution, although it is not normal distribution, we can still use linear regression equation because it's symmetric and parametric distribution. But a non-symmetrical or non-parametric distributions, we can't use linear regression function because all the linear regression functions are based around the mean, standard deviation. The concept of non-parametric distribution is based around the median. It is important to understand the concepts of mean and standard deviation. So the best and smallest thing one can perform is simply a look at the difference of means between experimental and control group, which is nothing but mean difference. Sometimes it can simply answer the question straight away if there's a significant difference. Or you can do a standardized mean difference. Standardized mean difference is nothing but if you divide the mean difference with that of standard deviation of all the participants, both control and experimental, that gives you SMD. So what exactly is standard deviation? If you look at the graph here, in the bell curve, you can see most of the data is distributed around the center, around the mean. But some data is spread both positively and negatively. -1 is -1 standard deviation. -2 is -2 standard deviation. +1 is +1 standard deviation. +2 is +2 standard deviation. The more the deviation, more they don't contribute to linear functions. They don't contribute on straight line on x and y graph. The outliers here, that doesn't contribute to the mean are nothing but residuals. The values that fall in the center are called predictors. So now I'm going to demonstrate how the predictors and residuals play in the linear regression equation. How do we deal with ordinal data? If you look at the picture here, there is a hierarchy from green to yellow to red. So when you